Hello, this is Mr. Henry, and welcome to lesson 1.5. Today we're talking about scientific notation. So the essential question says, how do I use scientific notation to represent very big and very small numbers? So this is the last lesson of the module, and the past couple lessons we've been talking about exponents. The first two we talked about rational and irrational numbers. So this is kind of like the culmination of a little bit of all of it. And for your warm-up in your Collins writing page in front of your packet, it is lesson 5, type 1. The question is, it says the mass of a proton is about 1.6 times 10 to the negative 27th kilogram. An electron's mass is about 9.1 times 10 to the negative 31 kilogram. Which do you think is bigger, the proton or the electron? And then why did you decide what you did? So I want an educated guess. I don't want you to say, oh, this one, and just move on. Don't just put down on your paper proton or electron. I want you to pick which one you think is bigger. Use a sentence. I think the proton is bigger because, and then give what and a reason why. Maybe you know from science class, maybe you know a little bit about scientific notation. We haven't learned this yet. This is literally what we're going to learn in this lesson. But I want you to take an educated guess. And then throughout the lesson, we'll see if your guess is correct or maybe fix your guess. Okay, so when you're ready, pause the video, answer the question on your paper, and when you're ready to move on to the vocabulary, hit play, and we'll move on. Okay? Now, scientific notation, we have one vocab word. The scientific notation is a method used to write very big and very small numbers. And I have an example down here, kind of like the algebraic notation, a times 10 to the n, where a is a decimal between 1 and 0, or I'm sorry, between 1 and 10, and n is an integer, being a positive or negative number. So 3 or 5 or negative 2, negative 8, those can all work for the exponent. And this first number, the a, being between 1 and 10, basically what it comes down to is it has to be a single digit number, or I should say one number in front of the decimal. So like 9.3 is great. 2.7 is fine as well. 83.2 is no good, because now you have two numbers in front of the decimal and you can only have one. So even if you had like a 10.3, that's no good, or a 0.2, that's no good. In this case, the 0 doesn't count as one of the digits in front of the decimal. You need a non-zero digit in front. So I'm going to start off by taking some numbers that are in standard form, just the normal way you would write a number, and we're going to write them into scientific notation. So the first problem here is 86,700,000. So the way we're going to write this in scientific notation is we're going to imagine we want our decimal to be right here. It's where we want it to be. So this number, if I imagine my decimals there, would be 8.67. You don't need all these extra zeros at the end of a decimal. So 8.67 times by 10, and it's always times by 10. That will always be true. Now, the exponent, the number that goes up here. A mistake a lot of people make is they count the number of zeros. So they'd go 1, 2, 3, 4, 5, and then throw a little 5 up there. But that's not how it works. The exponent up top here is how many places you would move the decimal from where it actually starts, which is back here, to where you want it. So this decimal would have to move 1, 2, 3, 4, 5, 6, 7 places. So it becomes 10 to the 7th power. And that's it. That number is now in scientific notation. Letter B. Letter B is a little bit different because now, instead of the number being a really big number, it's a really small number. It's 0.000032. But we can use the same basic method. We want the decimal to be right here. And so we're going to write the first part of our scientific notation, imagining our decimals there. So 3.2 times 10 to some power. Now, in this problem, instead of going to the right like we did in this problem, we moved to the left 7 places. Now we need to go from where we would start the decimal to where we want it. And we have to move to the right 1, 2, 3, 4, 5. And so we put a 5, but that's not quite right. So here's the only really trick you got to remember when you're dealing with scientific notation. And I'll try to put it as simply as possible. If you have a really big number, your exponent is going to be a big number, positive. If you have a really small number, your exponent is going to be a small number, negative. And that's it. That's how you can tell what your number is going to be in scientific notation. If you start out with a big number, a number bigger than 0, your answer, or I should say bigger than 1, your answer is going to have a scientific notation with a positive exponent. If your number in standard form is 0 point something, your answer is going to give you a number in scientific notation with a negative exponent. And the size of the exponent is how many places you would move the decimal from where it starts to where you want it. In this case, you moved 5 times, so it was a 5. In this case, 1, 2, 3, 4, 5, 6, 7 times, so it's a 7. Alright, let's see if you got it. Try these 2 problems, pause the video. When you're ready to continue, hit play, and we'll go through them together. Alright, first one. You should get, well, we want the decimal here, so it'd be 1.0 times by 10 to some power. Well, if it started here, 1, 2, 3, so it's to the 3rd power. 1.0 times 10 to the 3rd. Letter D. I want the decimal to be here because that gives me a decimal, or I should say a number, with 1 number in front of the decimal. So 2.56 times by 10, it's always times by 10, times by 10 to some power. So let's see. 1, 2, 3. But because I started with a very small number, my exponent is going to be small, negative. In letter C, I started with a big number, so my exponent is a big number, positive. So we now understand how to take a number in standard form and write it into scientific notation. The next example, we're going to do just the opposite. We're going to take a number in scientific notation and write it into standard form. So honestly, it's going to be just the opposite method. So I'm going to take this number, I'm going to write it down without the decimal, so 832. Now, I look at my exponent. I know my decimal needs to move 9 places from where it started. It started here. It needs to move 9 places, but because this is a small exponent, it's negative, my number in standard form needs to be a small number. And if I start moving my decimal this way, that becomes like 800, 8,000, 8 million, 8 billion. That's too big. I need a small number, so I'm going to move 9 decimal places to the left. That gives me like 0.000000832. That is a small number. So I count them out. 1, 2, 3, 4, 5, 6, 7, 8, 9 places. And all my empty places, I'm just going to fill in with zeros. So 1, 2, 3, 4, 5, 6, 7, 8 zeros. And if you're the kind of person who likes to put a zero in front, you can do that. So it's 0.00000000832. So that would be my number, and I personally like to pretty this up, get rid of my little loopies underneath. That would be my number in standard form. It's very, 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 very small, but that's what it is. Letter B. So I'm going to take this 3 times 10 to the 8th, and I put the number down first, so 3. And I know I need to move the decimal 8 places. And since this is a positive number, my number in standard form is going to be big. So I'm going to move 8 places to the right. So there's my decimal. 1, 2, 3, 4, 5, 6, 7, 8. 0, 0, 0, 0, 0, 0, 0, 0. Clean it up a little bit. And maybe even clean it up a little bit more. Start throwing some commas in there. So that gives me 300 million is my number in standard form. Go ahead and try letters C and D on your own. Pause the video when you're ready to continue, hit play, and we'll go through them together. Okay, so let's see. Well, since this is a big number, I'm going to be making my number in standard form bigger, so I'm going to move the decimal that way. So 3, 7, 4, 6, 3, 8. I'm moving 4 places to the right. 1, 2, 3, 4. Gives me right there. Hopefully you did not start at the end here and add 4 zeros and start going like that. No. You have to move from where the decimal starts, and you move the decimal 4 places. So since the decimal started here, 1, 2, 3, 4, puts my decimal between the 3 and the 8. Okay, 6, 3, 2, 3. Decimal starts here. Since it's a negative exponent, I'm going to be shifting to the left. 1, 2, 3, 4, 5, 6 gives me 1, 2, 3, 4, 5 zeros. So 0.000006323. And that's my number in standard form. So, really small numbers have negative exponents. Really big numbers have positive exponents. In standard form, the number in front of the 10, this piece, is always a single-digit number before the decimal. It could be a different number of decimals at the end. Like here it was 0.32. Here we had 5 numbers after the decimal. Here we had 3. Here we had none. But that number in front of the decimal always needs to be a single-digit number. If you could, please, how can you tell by looking at a number in scientific notation if the number represents a very big or very small number? Go ahead and answer that on your paper right now. Pause the video. When you're ready to continue, hit play. Okay, so hopefully what you said is if you have a number in scientific notation and it has a big exponent, this is a big number. If you have a number in scientific notation with a small exponent, negative exponent, it's a small number. That's how you tell. Positive exponent, big number. Negative exponent, small number. Now, scientific notation is just another way to represent numbers, just like using fractions or ratios or decimals or percents. It's just another way of writing a number. And since it's just another way of writing a number, we can still do some math. We can multiply, We can divide these numbers. And it's really not that terribly complicated. It's just a little bit ugly. So let's look at example A here. So I want to take 5.9 times 10 to the 4th times 3.8 times 10 to the 9th. Now, the first thing I hope you don't do, I hope you do not try to take this and write it out as like 5.9 or 1, 2, 3. I'm actually doing the math in my head here. Removing the decimal in my head. So 5, 9 with 3 zeros, and then times by 3, 8, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then try to take that in your calculator and multiply it out, because the first thing you're going to notice is it's probably going to give you an error. That number is probably way too big to put into your calculator and get an answer. But we can still do this just using a little trick or a way of doing it, a method. So here's what we're going to do. I'm going to take this, since this really, if I take my parentheses out, says 5.9 times by 10 to the 4th times by 3.8 times by 10 to the 9th, and I'm going to rearrange it. I'm going to put my decimal parts together. I'm going to put my powers of 10s together, and then we can do some math. So 5.9 times 3.8. 5.9 times by 3.8, and 10 to the 4th power times by 10 to the 9th power. So I'm going to take and I'm going to multiply the 5.9 times the 3.8. 5.9 times 3.8 equals 22.42. I'm out of space. I'm going to bump over here. 22.42 times by... Now, does this look familiar from the previous lesson? We have two powers with the same base. So to multiply these two together, we add the exponents. So we're at 22.42 times 10 to the 13th. That sounds like scientific notation. The only thing that's missing here is this first number is too big. We can't have 22. So if I move my decimal one more place this way, 2.242 times by 10, and now instead of being to the 13th, since we made our number, well, it was a bigger number, my exponent needs to go a little bit bigger. We moved one place, so our exponent gets one more number higher. 2.242 times 10 to the 14th is what this is. And that number is probably too big to fit in your calculator. But by using our properties, by doing the powers that we learned about in the last lesson, we know that we have the correct answer. Letter B. We're going to use the same basic idea. So here, we're going to separate it into two separate problems. We're going to worry about dividing this piece here and this piece here, just like we did yesterday, or on the last lesson. So I'm going to take my 4.73, clear, 4.73 divided by 8.4 equals 0.5630952. You know what? As far as we're concerned, let's just stick with like 3 numbers after the decimal. So 0.563. 0.563 times by, all right, now this guy, 10 squared over 10 to the 8th. Well, we didn't really look at this particular property yesterday, although there is a property that deals with this. But here's what you would do. To do math with these, to simplify them, you want to have them either both on the top or both on the bottom. I can tell you right now, having them both on the top is going to be the easier situation. So if I have 10 squared And remember what happens when I move him up top? This exponent changes sign from positive to negative. So it becomes 10 to the negative 8th. And now again, I have two powers with the same base. I add the exponents together, get 10 to the negative 6th. And this would almost be in scientific notation, except for my number out front again. It is wrong. It's not a single-digit number in front of the decimal. It's 0.5. I want it to be 5.63. So this number, look, it's small. It is less than 1. So to change this number to scientific notation, I have to move the decimal one place this way. So this becomes, oopsie, no 0. 5.63 times by 10 to the negative 7th. It's negative 7th because this number is small, and I had to move it one more place. So we come to the negative 7th. And if you're not sure if this is right, and I mean, I have doubts floating through my head that some of you might understand what I just did here. So what would happen if I write these both out? So this guy here, I would move the decimal 6 places this way, to the left. So 6 places of that would give me 5, 6, 3. 1, 2, 3, 4, 5, 6. From here, 1, 2, 3, 4, 5, 6 places. So I have 1, 2, 3, 4, 5, 6 zeros in front of my 5, 6, 3. If I do the same thing here, 5, 6, 3, now I move 7 places from here. 1, 2, 3, 4, 5, 6, 7. What you should see is I still have 6 zeros in front of the 5. So both this number and this number are exactly the same. But the bottom one is in scientific notation where the top one is not. If this doesn't make much sense, maybe 2 more examples would help out. So let's see here. So my first number here, I'm going to do the same thing. Can I move these? This gives me a bit more space to work, I think. So here I'm going to, again, separate. So I'm going to take my 6 times my 1.35. So I'm moving my decimal terms together, times by 10 to the negative 3rd, times by 10 to the 6th. I don't like using the x for multiply, but I guess it fits in this case with scientific notation. I'm going to multiply these guys and multiply them. So, clear, clear. 6 times 1.35 equals 8.1. 8.1. I like that because that's already part of scientific notation. I have one number in front of the decimal, which is awesome. Now, the powers of 10. Same base, add the exponents. Negative 3 plus 6 is 3. And would you look at that? We're done. 8.1 times 10 to the 3rd. Okay. Letter D. Same thing. I'm going to split it up. Worry about my decimals, then worry about my powers of 10, and we'll go from there. So, decimals. Get out of here. No. Alright, so clear. So we got 5.6. 5.6 divided by 3.3 equals, we've got 1.69696969. So how about we say 1.69? Yeah, repeated. Times by, alright, so again, we're going to move this guy up top, which becomes times by 10 to the negative 2. And now we add the exponents together. So 4 plus a negative 2 is 2. And there we are, in scientific notation, 1.69 times 10 squared. Hopefully now it makes a little bit more sense, because I've got, well, a few I'd like you to try. So please, pause the video. Please try letters E and F right now. When you're ready to continue, hit play, and we'll go through them together. Alrighty, let's give it a whirl. So I'm going to take my 9.8 times by my 1.5 times by 10 to the negative 2 times by 10 to the negative 3. I'm going to do the powers of 10 first. That gives me 10 to the negative 5th, because I add the exponents together. And over here, I don't know, clear, 9.8 times 1.5 equals 14.7. Now, that unfortunately is not in scientific notation. So we're going to have to do one step. Now look, this number is bigger than 1. So for me to move this in scientific notation, my exponent has to get bigger by 1 place. So 1.47 times by 10. Now, what is one number bigger than negative 4? I'm sorry, I gave the answer. One number bigger than negative 5, which is negative 4. So negative 4 is bigger than negative 5. If you think about it on a number line, negative 5, negative 4, negative 3, negative 2, negative 1, 0. Negative 4 is bigger because it's closer to 0, and going this way, you get bigger. 1, 2, 3. Letter F. One piece at a time. I'm going to do the 8 divided by 6.6. Clear. 8 divide 6.6 equals 1.21 repeated. 1.21 repeated. Times by, alright, so this guy moves up top, gives me 10 to the 5th. They have the same base, so I add the exponents, giving me 10 to the 3rd. And my first number already is like 1 point something, so this is in scientific notation, and we're done. Hopefully it's sinking in. You're starting to understand a little bit better. You've got 2 more. So go ahead and pause the video. Try these last 2 problems out. When you are ready to continue, hit play, and we'll go through them together. Okie dokie. So first one first, I'm going to do the same thing and separate the decimal parts. 1.1 times by 3.56, and the powers of 10. 10 to the 13 times by 10 to the 22nd. That gives me times by 10 to the 35th power, which is huge. And that gives me, I have no clue, 1.1 times by 3.56 equals 3.916. Let's see, this number out front already has 1 number in front of the decimal, so this is in scientific notation, which means we're done. Lastly, letter H. I'm taking my 1.68 divided by 7.2 equals 0.23, repeated, times by, let's see, he comes up top, becomes 10 to the negative 14th, cancels here, the bases are the same, so you add the exponent, gives you 10 to the negative 4. Alright, since this number is less than 1, it's a small number, my exponent, my power here, my exponent is going to have to get smaller by 1 place so I can turn this into scientific notation. So, 2 2.3 times by 10 to the negative fifth. And checking this number out, it is now in scientific notation, and we are done. So, that's all the computational stuff. We now know how to multiply numbers with scientific notation. We know how to divide them. We know how to write numbers in scientific notation. We know how to take numbers in scientific notation and change them into standard form. The next 4 problems are going to be the applications, where we take those skills and use them in more real-life scenarios. So here in example A, it says, Mr. Einstein's class is studying how light moves. The speed of light moves approximately 671 million miles per hour, which, by the way, is true. Express this number in scientific notation. Alright, so this one's pretty easy. I mean, it's a depth of knowledge 1, which means there's not a whole lot of planning you need to do. It's just kind of a straightforward sort of problem. So I'm going to take this, turn it into scientific notation. So 6.71 is what I would like. I want the decimal here. And that decimal has to move 1, 2, 3, 4, 5, 6, 7, 8 places. And because this number started out as a big number, I know my exponent is going to be positive. I am done. Nothing else we got to do. That one was pretty easy. Number 2 says Samantha was calculating the population of the United States. After her calculations, her calculator showed 3.1 EE8, as you can see. She then calculated population of the world and got an answer of 7 EE9. Samantha wants to know how much bigger the population of the world is than the US. So one of the standards in the Common Core is that students should be able to recognize what a number looks like in scientific notation if it's given by a calculator. And this is one of those methods. So this 3.1 EE8 is the calculator's way of saying 3.1 times by 10 to the 8th. And they use this EE notation just because it takes up less space. I mean, this would be harder to put into a calculator, program a calculator to show, especially like a dinky calculator like this. I mean, if I do 3.1, times by 10 to the... It doesn't show it right. I mean, we can't even show exponents very well here. Okay? So that's what this is showing. It's 3.1 times 10 to the 8th, and this would be showing 7 times 10 to the 9th. Just so you're aware, you could also, if it had a negative 9, it would just make the exponent negative. Okay? So we now know how the calculator might show. There's a couple different ways the calculator might show this. I think there's one way that has, instead of 2 E's, there's just 1 E. But you kind of get the idea. But now the question is, Samantha wants to know how much bigger the population of the world is than the US. So if you're trying to find out something like that, how much bigger? You're usually looking for something that's like 3 times bigger or 5 times bigger. In that case, this is what's called an order of magnitude. And we've actually done this problem a couple times already, just not in this format. We need a ratio, a fraction. So we're going to set up the world population over the US population. So 7 times 10 to the 9th, 3.1 times by 10 to the 8th. And if we do the same thing we did in the past couple problems, we're going to get an answer for about how much bigger the world population is than the United States. So let's see. This gives me, if I take clear, 7.1 divided by 3 equals 2.36. 2.36 times by 10, that is not a 6. Okay, times by 10 to the, let's see, this guy comes up top, becomes 10 to the negative 8. I add the exponents, gives me 10 to the first power. Okay, and if I simply would actually multiply this out to make a number that's a bit easier to understand, that gives me 23.6. All right, so the world population is about 23.6 times the United States' population. And that's what we found. So this order of magnitude, how much bigger, how many times bigger, the way you would do that is you would set up a ratio. Like, for example, if you had, think of an easier example. If you had a sandwich that was 8 feet long and another sandwich that was 2 feet long. So how many times bigger is the 8-foot sandwich than the 2-foot sandwich? Well, if you do the math and you simplify this, you find out it's 4 times bigger. That's kind of what we did. The world population over the United States population, we divided, and we found it's 23.6 times bigger. Now, I have 2 more of these problems for you to try. The first one says, after studying the speed of light, little typo in there, or I just can't read, after a study of light, which is 617 million miles per hour, in Mr. Einstein's class, the next topic was the speed of sound. The speed of sound is 762 miles per hour. How much faster is the speed of light than the speed of sound? Express your answer in scientific notation. So, try to find out how much faster the speed of light is than the speed of sound in scientific notation. Pause the video. When you're ready, continue, hit play, and we'll go through it together. Okay. So hopefully the first thing you thought of is, I need to do another one of those ratio things to find out how much faster, how many times faster. We need a ratio. So how much faster is the speed of light than the speed of sound? So the speed of light is that 6.17. I'm taking this into scientific notation. Makes it easier. So 6, and actually we did this problem. I can just copy it. 6.71, and here I say 17. Now I don't know which one's true, but either way, times by 10 to the 8th. 6.17 times by 10 to the 8th. And the speed of sound is, let's see, 761.2 times by 10 to the something. So let's see. I need to move the decimal 2 places. And since this is a big number, it's a positive exponent. 7.612 times by 10 to the second. And now if I simplify this ratio, if I divide it, I'll find out how much faster the speed of light is than the speed of sound. And by the way, I looked it up. The speed of light is actually the 671 million, not this 617 million. But we'll continue with the problem the way we have it. So let's see. So we're going to divide. And actually, I lied. I don't want to leave it the way I have it. I want to do it right. I'm not going to be lazy. And I'm going to divide. So I'm going to take, clear, 6.71 divided by 7.612, 0.88 times by Alright, this guy goes up top, becomes 10 to the negative 2, and I add the exponents, giving me 10 to the 6th. And this would almost be good, except that first number is not in scientific notation. So I'm going to take that, and I'm going to make it better. So this is a small number. So I need to take this number and change it to scientific notation, which means this number is going to become smaller. So that becomes 8.8 times by 10 to the smaller would be 5. This is actually our answer in scientific notation. This is how many times faster the speed of light is than the speed of sound. Now, if that doesn't make much sense, if you don't like it, this is the answer, but a little extra. And standard form, that gives us 8, 8, 1, 2, 3, 4, 5. It's about 880,000 times faster than the speed of sound. Just so you're aware. Alright, so, letter D. It says, using a radio telescope, you observe what appears to be a star exploding in a nearby solar system. Using the information you found in part C, if the star is 1.88 times 10 to the 17th miles away, and it took the light 32,000 years to get to Earth, how long would it take for the sound of the explosion to reach Earth? Express your answer in scientific notation. Okay, so just to make sure I have all my information on the right page, we found in letter C that it's 8.8 times 10 to the 5th, or light travels 8.8 times 10 to the 5th times as fast as sound. So that was the information from part C they're talking about here. So go ahead, pause the video, do it on your own. When you're ready to continue, hit play, and we'll go through it together. Alright, so what makes this problem more difficult, I believe, to DOK3 is the understanding of the scenario. So here's Earth. Here's this other star. Earth looks pretty bad. I'll just fill it in. We're the water planet after all. There you go. Earth, star. So we know the star is 1.88 times 10 to the 17th miles away. And it took the light. So when this star exploded, boo, it took the light 32,000 years to reach us. How long would it take for the sound? So there's the light, and here's the sound waves. How long would it take the sound to get to us? So that's the question. If this helps you understand, and maybe you're really stuck before, maybe repause the video and try it on your own now. If not, well, let's do it. So the hard thing to understand here, or the thing that I feel is hard for you to understand, is if the light travels this much faster than sound, then the reverse is also true. Sound is this many times slower than light. So if it took light 32,000 years to get to Earth, it would take the sound 32,000 times this. This is how many times slower it travels. So, I mean, make a very simple example. If it took the light 1 year to get to Earth, and sound travels this much slower, it would take sound this many years to get to Earth. But it took the light 32,000 years, so we're going to take this number times by 32,000. So here's how we do this. So I'm going to take 8.8 times 10 to the 5th, that's scientific notation, times by 32,000. And it says you want your answer in scientific notation. You know what I'm going to do? I'm going to go ahead and change this 32,000 into scientific notation. That way I can use the properties we learned earlier. So I'm going to take this. That's 3.2 times by 10 to the 1, 2, 3, 4th power. And this is just 8.8 times by 10 to the 5th power. Now, I'm going to rearrange. I'm going to move my decimal guys together. 8.8 times by 3.2. I'm going to move the powers of 10 together. 10 to the... Oh, that's not a 10. That's an x. Try it again. 10 to the 5th times by 10 to the 4th. Now, I'm going to multiply these and multiply these. This side I'm going to use a calculator for, so I don't want to do it in my head. So I'm going to take 8.8 times 3.2 equals 2816. 2816. Oh, I didn't see what the decimal was. 28.16. All right. Times by. Since these powers have the same base and they're being multiplied together, I add their exponents. We learned that back in lesson 1.3, so that is 10 to the 9th power. And this would be done, except this first number is not a decimal, or it's not a decimal between 1 and 10, which means this is not scientific notation. So one more little step gives us 2.816 times by 10 to what power? Well, this number is a big number, which means our exponent is going to get bigger. That is how long it would take the sound of the explosion to reach Earth. And just to write it out for show, 2816 and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 years. So that is, let's see, hundreds, thousands, millions, billions, 28 billion years. And no, we would not actually hear the sound. Sound dissipates in waves, and there's no waves in space. There's no particles in space for the sound to travel from one planet to another or one solar system to another. So we wouldn't actually hear the sound. But if we could, maybe the gravitational waves, which there are, would take, well, gravitation travels at the speed of light. Never mind. It would take sound this long. Okay? I was trying to be smart and I messed it up. All right. Summary. So this is lesson 5. This is a type 1. This should probably be the last Collins writing space you have on your paper. I believe there's 10 spaces, and if you've done all your warm-ups, this would be the 10th one. It is a type 1, so I'm grading on completion. Make sure you did the task. It says here, why is scientific notation used when talking about really big or really small numbers? So we talked about it in this lesson. I want your opinion. Why do people use scientific notation? This is not just something for math class or something for science class. There's actual people out there that use this stuff. Why do you think they do it? Okay? So, go ahead, pause the video if you need to see the question longer, answer the question in the Collins writing page at the front of your packet, and then we're done. This has been lesson 1.5. Thanks for watching.